One thing that I want to address right away, we saw at the end of last class the bromination mechanism, and then somebody brought up to me that the bromination mechanism in the online textbook that I have linked to our Canvas page is not the same as the mechanism that I demonstrated for you guys. So I do want to make something clear. I will be grading you guys on your mechanisms, so I want to make sure we're on the same page. I don't want you to feel like you can learn from one resource and not another if they show different things and kind of be in the same spot. So if you do follow this link to the McMurray free text and you go down to the chapter on aromatic substitution, EAS, the first mechanism they actually give you is the mechanism for bromination. What you'll notice is they have no arrow pushing for the reaction between bromine and iron 3 bromide. They just show it being converted to a bromonium ion and an iron 3 bromide complex. And then they say the lone pairs just bond to the bromonium ion. Now, a good mechanism is a plausible mechanism. It means that you could see that happen. I don't know that that feels plausible. Bromonium ions are not necessarily easy to make. They're incredibly reactive. And that makes me think that this species, where it's split into two ions, I'm not sure where they got this hypothesis. I've not seen this before, except for in this text.
Yeah, I thought it was a bit high.
Which is fair, and I see where you came from, because some of you tried to tackle your mechanisms before you even came into class. I would recommend not showing this. How many steps did we have yesterday in our mechanism?
4, 8,
6.
Not 6.
This one.
3.
Oh no, it's this one.
3 steps.
3.
Oh, we did see 6 types of reactions, but our mechanism had 3 steps. Activation of the electrophile, which is what they're doing here, but they don't have any electron arrow pushing, and I don't agree with their activated electrophile. Then, addition, the ring acts as a nucleophile. We get our resonance forms, and then that is followed by elimination. And guess what? They don't do a great job of showing elimination either. What they've got here is the negative charge from FeBr4 minus attacking the hydrogen and that bond going back to reform aromaticity. Their byproduct is HBr. So they're indicating that something with excess electrons here is using its electrons, and then later they inform you that was bromine. What I had you guys do instead was actually indicate, did you know the negative charge is on iron? But that doesn't mean that iron is using the excess electrons. Iron will lose the excess electrons and become neutral again by bromine taking the electrons away from it to do the deprotonation step. So I would like you to avoid showing anything like this, because I don't think that it is clear enough that you understand what atoms are using what electrons to do what, and I would rather you see something like this. Now, I know that I'm not necessarily perfect at putting mechanisms on the board. I make mistakes sometimes too. But my recommendation to you would be get to know the steps that I put up. Don't try and reinvent the wheel. And if you do find other resources to try and study off of, compare what is similar, see what is different, and then try to lean into my side of the difference. Because if you gave me something like this, there are similarities. The excess electrons are attacking to do the deprotonation. But there is differences. This highlights how the electrons are moving, and this does not. And if you have questions that come up and you're like, I don't know if I'm doing this right because I found this here and I don't know if it's similar or different enough, send me a message, send me a screenshot, bring it up in class. We'll talk about it.
Wait, but you said that on the homework, the bromination is different than...
Yes, and well, on the homework, the mechanism is different because it's not just benzene that's being substituted, it's phenol that's being substituted, right?
What?
Is the starting material on the homework
Oh, yes.
Benzene?
It is.
Or is it-
It's fat.
Yeah.
Phenol.
hydroxybenzene?
Yeah.
Which means it's not going to be exactly this mechanism. Because,
Pretty similar, though, right?
yes, but the substituent on benzene will not play a role. It's going to be involved in the mechanism. Okay. I want to keep moving along. We'll look at the chlorination mechanism, alkylation, and then acylation. Now, I told you guys last week, I showed you bromination had 3 steps. Chlorination also has 3 steps. I'm going to show it sequentially this time, rather than giving it to you in those individual steps. I want you guys to have a perspective on both ways that you can show a mechanism, and I want you to choose which one you like better. The step-by-step is a little bit cumbersome because you draw a product and then you rewrite it. You draw a product and then you rewrite it. But the full sequential mechanism is a little cluttered because every time you draw a product, you show it with reaction arrows doing something else. Okay, so we have benzene, which will not react in this first step. And then we have chlorine and the catalyst aluminum chloride. We see the same thing that happened with bromination. Chlorine forms a bond to the aluminum, which creates this complex. And if you like to see the aluminum kind of in this sterically hindered environment, you could write it as AlCl3 minus, or you can draw out those chlorines because then it reminds you the positively charged chlorine is not the one that's attacked. The positively charged chlorine is not as accessible as this terminal chlorine. I do also want you to pay attention. I used my circle again in the first step, but I went away from the circle in the second step because now the electrons are important and I need to highlight those pi electrons. Does it matter which of these pi electrons I use to attack? No, it doesn't. So I attack from any of them. I attack the terminal chlorine, break the chlorine-chlorine bond, which establishes AlCl4 minus. Just abbreviating it there because I don't need to see it in depth. Caesar?
So let's make sure that that arrow that goes from there, you want it
From the inside electron?
Yeah.
Good question. I'd take either. I'd prefer that it start by the bonding region and not by the atoms themselves. But you can see mine came from the inside line. It doesn't have to. As long as you indicate electrons from this pi bonding area are going, that's good enough. Now, does it matter which carbon I add the chlorine to? No. In this case, they're all the same. So I'm going to pick this carbon on the bottom. And what happens to the other carbon that was holding that bond?
Positive.
Takes on a positive charge. This is EAS. The sigma complex is positively charged. Now I see some resonance. I go from high electron density to low electron density. My low electron density in this molecule is the positive charge. So now my positive charge bounces around my structure. How many resonance forms in total do I get for this reaction? I get 3 resonance forms. Now, at the last resonance form, what did I forget on my last resonance form? Yeah, I forgot my positive. On my last resonance form, I'm going to redraw my catalyst. Well, it's not quite my catalyst because it's bonded to an extra chlorine. I'm going to redraw it similar to what I did with bromine and the bromine catalyst yesterday. I'm going to highlight this Cl-Al bond. That bond is going to break in this last step. Who owns those electrons, chlorine or aluminum? You're not used to thinking about the electronegativity of aluminum, are you? Well, it's not very electronegative, which is actually why it acts as a Lewis acid so well. It accepts electrons because it's not very electronegative. Maybe that didn't make sense, actually. I mean, it's in the same family as boron, so it's got the capacity to accept electrons. Chlorine will take the electrons. Chlorine bonds to the hydrogen. The CH bond goes back to form the pi bond, reforms aromaticity. Gives me a byproduct of HCl, and I regenerate my catalyst, AlCl3. I want to point out a small detail in this mechanism that I've done to try and set you up for success. As soon as the ring acted as a nucleophile, I drew in the hydrogen. I drew in the hydrogen at the carbon that acted as the nucleophile. Do you guys agree? The hydrogen that is drawn in is from the nucleophilic carbon. This carbon used its electrons to bond to chlorine. Why did I highlight that carbon? Or that hydrogen on that carbon? Because that is the hydrogen that needs to leave. That's the hydrogen that needs to be removed. So it's important I pay attention to it. But also, what's the hybridization of that carbon? sp3. This is the carbon that breaks conjugation. This is the carbon that will never be involved in the resonance form. This is the carbon, if I don't draw in that hydrogen and the new electrophile, I might forget that there's a hydrogen there, and I might assume that it's sp2, and I might accidentally draw a resonance form that involves it. So, my advice, I don't know what to call it necessarily, draw in the nucleophile's hydrogen. That will remind you that this carbon breaks conjugation, this carbon is not involved in resonance, and that carbon needs to be deprotonated. Okay. Let's move on to alkylation. Do you guys remember the names of the chemists that alkylation is credited to? Friedel and Crafts. Yep. Yesterday I gave a mechanism with 1-chloropropane forming an isopropyl group. Do you guys want to see the same? Do you want to see the mechanism for that? I think it's probably worthwhile so we see the carbocation rearrangement. Well, wouldn't you know it, the aromatic ring doesn't play a role in the first step. Instead, the alkyl chloride bonds to the aluminum via the chlorine, just the same as last time. Can you guys tell me what charges appear now?
Positive chlorine and negative aluminum.
Good. Same as here, right? Chlorine's got 2 bonds, positive. Aluminum's got 4, negative. Now here is a deviation from the chlorination and bromination mechanism. Chlorine will actually hop off. Why do I say that's plausible here, but I say it's not plausible here? Look at the cation that I generate. Do I generate a carbon cation? Or, excuse me, do I generate a chlorine cation? Your textbook, or the online textbook, recommended that this bond break and it leave behind a Cl+. Have you ever seen a Cl+ ion? Not by itself. I've never seen it until that textbook. But here, do I generate a Cl+ ion? No. I generate a carbocation. And how many times have you seen that? A lot. So this is much more plausible. But we go back to our OChem 1 days and we say that's a primary carbocation adjacent to a secondary carbon. This goes through a carbocation rearrangement. So chlorine attacks aluminum, chlorine pops off, and I form my carbocation. My carbocation is the activated electrophile. It's now more electrophilic than my alkyl chloride was at the beginning. Of course, because it rearranges, we really only see it here. Activated electrophile. By the way, this also activated electrophile. I'm just saying that because it would have taken the electrons, it would have been electrophilic anyways, but the catalyst has activated it to make it even more electrophilic. Okay, now in this step, the aromatic ring attacks the carbocation. Because we're dealing with benzene, it doesn't matter which pi bond I take. It doesn't matter where my group goes, but I will recommend that you draw in the nucleophile's hydrogen because it reminds you the other carbon takes the positive charge and this carbon is never involved in resonance. Now, I'm in a resonance structure. I did tell you guys, I'm not grading on these boxes, but I like to use the boxes to remind me everything within the box has resonance arrows, and everything within the box is the same molecule, just a different perspective on it. High electron density to low electron density, I move my pi bonds towards the positive charge. One more resonance form. At the end of my resonance structure, I'm going to highlight AlCl4 minus again. Oh, I'll let you guys catch up, and then I want you to spot the mistake I made up there.
The one extra chlorine.
Yeah. Yeah, I put AlCl4. I should have put AlCl3. Now, I really don't want you guys to think that I get super nitpicky with details in your mechanisms, but I do want to make sure that we clarify what are important and what are not important details. Something that's not so important here is this box. So I can actually show my next step going through that box, because that box is really just my reminder that this is a resonance form. Chlorine takes electrons back, deprotonates hydrogen. The aromatic ring reforms. And I have isopropyl benzene with an HCl byproduct and aluminum trichloride byproduct. Sam.
I have a question. Is this an example on some of the homeworks? It was like asking, well, one question was like, which of the following best describes an alkyl substituent effect in an electrophilic aromatic substitution? And it was like activating versus deactivating ortho, para, like meta.
It's not.
Okay.
And we're going to get into activating effects and directing effects after we get through these mechanisms. But here's the idea. In these mechanisms, we're taking benzene and reacting with something. In order to have an activating effect and a directing effect, we need to have a substituted benzene. So let's say that I take isopropyl benzene and I react it with chlorine in aluminum trichloride. The isopropyl group, the alkyl group, is going to change the nucleophilic character of the ring. There's 5 other positions that can be nucleophiles. They're not all equal in their nucleophilic character. It changes the nucleophilic character and it directs certain positions to be more nucleophilic. So we'll look at that next. Is there another question?
Yeah, so it throws me off, but I'm guessing it doesn't matter. Like every time, like at the end when you're using the last resonance form, like if you look at the bonds, they were reformed in different places, but then when you give a final product, like obviously you can just put a circle there.
You could just put a circle. And so you could put the 3 double bonds in any position because they're both resonance forms of each other. I'm glad that you pointed that out. My double bonds are in different places based on how I drew my arrow and how I drew my final product. You're absolutely right. But we also know the placement of the double bonds doesn't matter. So the reason I'm glad you brought that up is so that we can recognize doesn't matter with your aromatic rings. It doesn't matter how the bonds are shown. They're all identical. And so do you think adding the circle actually helps you make better sense of it? Fair.
I mean, I understand now, but like in the mechanism that I did for a homework, I think there was what I tried to figure out how to do the OH, and on that one I had to reform the whole thing, so I'm not sure if it did right now. But it's alright.
Well, you'll have a chance to go back and check it.
Right.
Okay. Let's look at our acylation mechanism. Correct me if I'm wrong, but we added a 3-carbon alkyl group that was bonded as this straight chain and then ended up as a branched chain. In our acyl group, we also added a 3-carbon chain, but it never rearranged, it never branched. So it tells us that alkylation and acylation have fairly distinct mechanisms. Our first step in acylation, believe it or not, is the same as our first step in alkylation, which is the same as the first step in chlorination, which is essentially the same as the first step in bromination. That creates a negatively charged aluminum, a positively charged chlorine. We have essentially turned the chlorine into a good leaving group, just like we did last time. Chlorine pops off of the carbon. Here, chlorine pops off of the carbonyl carbon. Now I'm going to show you guys a resonance form because I think it's useful to understand the resonance here. I'm also going to do it a bit incorrectly at first so that it helps you make sense of the change that we're seeing. The aromatic ring, of course, is always in resonance with itself. But this carbonyl carbocation is also in resonance, which is a reason that it forms so readily. I've drawn it wrong, though. I've drawn it in a way that probably makes more sense to you. What is the hybridization of this carbon? No, wait, take a step back. What's the hybridization of this carbon? sp2. Take away an electron environment. sp. And what is the molecular geometry of an sp hybridized atom? Not planar? Linear. So the way to actually draw this 3-carbon chain is with a linear carbocation. That's what it truly looks like. And this carbocation, like all carbocations adjacent to a heteroatom, this carbocation is in resonance with the oxygen. I will accept showing one or both of those resonance forms. You don't have to show me both of them in your mechanisms. But you very well could see questions that say, which are the 2 resonance forms of the activated electrophile for acylation? You guys agree I can just point at the box there, right? Because that resonance box means one compound. That compound is the activated electrophile. Okay, here's a question. Which of those resonance forms is more stable? And which one is more reactive?
The right is more stable.
We got 2 different answers. Can I hear your thoughts?
Right.
Maybe no.
Carbon is a secondary, and the oxygen is a primary.
Okay.
So it'll be
Primary versus secondary, more substituted, more stable. Jenny first, and then I'd like to hear Caitlin's too.
I just thought because the oxygen has a positive charge, I feel like oxygen is more willing to have a charge versus carbon, but I could be wrong.
So you think oxygen's more willing to have a charge regardless of the charge?
I know it's more electronegative, so I would prefer
It would.
a negative charge, but I don't know.
Okay.
This is my thoughts.
This is what we call chemical intuition. You guys are feeling something in your gut, and you're like, I feel like when I see a charge, it's always on oxygen, never on carbon.
Yeah.
Caitlin?
Wouldn't the left one be more stable just because they all have octets, which is more important than charge?
That's it. We have 3 rules for resonance structures, which is minimize charge, can't be done, maximize octets, that's done on the left, and then place charge appropriately. But we've maximized octets on the left. The charge would be more appropriate on the carbon because it's a positive charge and oxygen is more electronegative.
Okay.
But because there are full octets on the left, that's a more stable resonance form. What that means is this resonance form is the reason this intermediate forms so readily. But this resonance form is the reason that it reacts. But guess what? You can show reaction happening from any resonance form. And I'm asking you guys not to do what with your resonance forms? Don't double up on them. So if you want to show both resonance forms of this electrophile, then you have to attack the second resonance form. You can't show arrows on the first resonance form that generates the second, and then also show arrows attacking that resonance form. That's doubling up, and your arrows no longer make any sense. You're not proposing anything that's plausible anymore. So because I've shown this resonance form, I'm going to show it attacking the more stable. It's going to attack at the carbon position, which breaks the triple bond back open to O. That is essentially the same as if I hadn't drawn it and I just attacked the carbocation. So there are 2 correct answers, 2 correct ways to do this. And in case you'd like to see what it looks like on the other side without drawing the other resonance form, it just looks something like this. Just like when the ring attacked the carbocation. Okay, now I've chosen to go with this top left, although to be fair, I could draw at any position. I've used a specific electron pair, but this ring is totally symmetric. I could draw it anywhere. It's going to look a little different than how we drew it yesterday in class. I'm going to draw it off to the side here. And I'm going to draw that nucleophile's hydrogen, because then I'm reminded of where to place my positive charge. And this is also in resonance. Pi bond moves to carbocation, high density to low density. Carbocation rearranges. High density to low density. Carbocation rearranges. Rearranges is actually a bad word there, sorry. Kind of makes it sound like I'm saying there's a carbocation rearrangement, which is very different. And then I'm going to highlight AlCl4 minus by showing the AlCl bond. And remember, we said the last step could go by 2 names. This step is elimination. Exactly. Elimination, aka deprotonation, aka reformation of the aromatic ring. Chlorine takes its electrons, bonds to hydrogen. CH electrons go to form the aromatic ring. And I've intentionally left an error on that final product.
There should be another carbon.
Missing a carbon on my acyl chain. How easy do you think it is to lose a carbon during a mechanism like this? Where you go from this carbonyl to this carbonyl cation? Pretty easy. And then when you attack a carbonyl cation and now you've got to draw it back on the ring, it can be really easy to lose carbons. So what's a technique to avoid losing carbons? Count your carbons. Or as I like to say, map your carbons, which is counting, but then also bringing them throughout. So I might count this as 1, 2. I could count all the way to 3, just don't know how to count that high. No, I can count that high, but I don't really need to, because if I recognize that 2 has a methyl group coming off of it, that's all I need. 1, 2, methyl group. 1, 2, methyl group. 1, 2, methyl group. And that way I can make sure that none of my carbons get lost in the mechanism. Okay, questions? You see the similarities in each mechanism. You see the distinctions. Bromination and chlorination, how similar are they? Like almost identical. Alkylation and acylation, how similar are they? What's the biggest difference between the two? Alkylation has the possibility for carbocation rearrangements. Doesn't mean it always will. Imagine if I started with 2-chloropropane. Doesn't need to rearrange now. Acylation never rearranges. It's actually got this resonance stabilized intermediate. How are you feeling on your electron arrow pushing? Do you feel like there are things that you saw up here that you think you know, but you might have gotten mistaken? Okay. Well, that's what the homework's for anyways, so I can find those little details. I'll tell you what you're doing well, and I'll tell you if there's any improvement I want to see. Okay, then let's carry on. We are looking right now only at EAS reactions, but we're going to move from EAS on benzene to EAS on substituted benzenes. I'm going to give us just a quick energy diagram. Here's energy. We call this reaction coordinate, which means I'm looking at something on the left like my starting material and something on the right like my product. In this black line, I'm going to look at just benzene. With this green line, I'm going to look at an electron donating group that is on benzene. And with this red line, I'm going to look at an electron withdrawing group. I think if I had given myself more space, I would have drawn 3 different benzene rings. Benzene, benzene with electron donating, benzene with electron withdrawing. Hopefully this makes sense. If not, I'll try to resketch it so you guys can make sense of it. Benzene requires a certain amount of energy in order to form the sigma complex. Do you guys remember what the sigma complex was? It's this one, yeah. It's this complex that's in resonance. It's the benzene ring when it's not a benzene ring. And you guys agree it takes some amount of energy to do that? Benzene has to take its electrons and attack the nucleophile, and then it forms this higher energy intermediate. Let me clarify. how is the ring behaving here? Is it behaving as a nucleophile or an electrophile? Acts as a, let's make sense. Make sure. Attacks, nucleophile. Attacks, nucleophile. When it acts as a nucleophile, the electron donating groups activate its nucleophilicity, which means that it requires less energy and forms a more stable sigma complex. So we say that electron donating groups are activators towards EAS. Why do they make the ring a better nucleophile? These are groups that have lone pairs of electrons and or they're alkyl groups and they just have like electron moral support. And they share that electron density with the ring. So now the ring has more electron density to go and attack with. It requires less energy. It forms a more stable sigma complex. That means it's easier for the reaction to occur. The ring has been activated. This is very similar to what I'm saying here with activated electrophile. These groups are electrophilic, but now with this catalyst, they're even more electrophilic. What's going to happen with my electron withdrawing groups? Electron withdrawing groups do what to the ring? They pull electron density out of the ring. Well, the ring needs that electron density to be a nucleophile. So if the electron withdrawing group pulls it away from the ring, then the ring has less nucleophilic character. So we say that electron withdrawing groups and halogens. You guys remember that halogens didn't fall into the family of EDG or EWG? They're going to play the middle game. Electron withdrawing groups and halogens, these are called deactivators. I do want to be clear. I'm saying electron donating groups are activators to EAS reactions. And electron withdrawing groups are deactivators to EAS. But EAS is where the ring acts as a nucleophile, takes on a positive charge. NAS, the ring acts as an electrophile, takes on a negative charge. So these effects are going to flip when we talk about NAS reactions. Okay, this is the activating effect. But not all groups activate equally. On a polysubstituted ring, the strongest electron donating group is the strongest activator. Sorry, I'll give you guys some time. Oh man, it's hard to stop, you know? What questions do you think I'm going to ask here? So what do you think, Caesar? In this polysubstituted ring, which is the strongest activator? Which group makes the ring the best nucleophile it can be? The NH2? Do you guys agree? Why do you agree? Because it's in my notes. Because we looked at it yesterday. Why does nitrogen activate better than nitrogen? Think about that.
Smaller.
Why does the nitrogen of the amine activate more than the nitrogen of the nitro group? I mean, they'd be the same size, right?
With the hydrogens.
No, it's not it.
Is it because NO2 is the withdrawing group?
That's right. So NO2 is a withdrawing group. What we don't see here is that NO2 actually has a pi bond. There's an NO double bond. And electron withdrawing groups often have pi bonds connected to the ring that pull electron density out. We also don't see, but NH2 has a lone pair. So these nitrogens are not connected in the same way. One has a lone pair that it can donate to the ring. One has a pi bond that it can use to pull electrons out from the ring. So they are both nitrogen, but they are not bonded in similar ways at all. And why is nitrogen in the amine a better activator than oxygen in the ether? Oxygen has a lone pair to donate, correct? Oxygen is electronegative, correct? That's the reason why. Oxygen is more electronegative than nitrogen. So oxygen can share its electrons, but if nitrogen wants to, why stop it? Nitrogen shares better than oxygen, so nitrogen activates the ring best. Okay, now what am I going to ask in this series of molecules here? Rank them in order of their reactivity to EAS. Rank reactivity to EAS reactions. Which of these is the least reactive to EAS? Which is to say, which of these requires the most energy to form the sigma complex? The sulfonyl group. Why? It's electron withdrawing. Why is it electron withdrawing? It's got pi bonds from the sulfur to the oxygens, which pull electrons out. Which of these is the most reactive to EAS? Which of these requires the least amount of energy to form the sigma complex? Terbutyl. The alkyl group activates, not by a lot, correct? I mean, it doesn't activate as much as oxygen does. It doesn't activate as much as nitrogen does. And the sulfonyl group is a deactivator, which means we are looking at it already from highest reactivity to lowest reactivity. Benzene is literally the template. Benzene is the reference point. Now you start adding all of these other groups on there, and you see how it changes relative to benzene. Okay, any questions so far? That's our activating effect, by the way. And I don't want to trick you guys, but we can start adding multiple groups on there. So rather than saying I don't want to trick you, then it sounds like I'm going to trick you. Let's do another ranking one. Let's make this one a little bit more complicated. 4 benzene rings. I've got OCH3OH, CH3OH, CH3NO2, and CHO NO2. Now let's rank their reactivity to EAS.
And that CHO is the carbon one that is bound, or is it oxygen?
Yeah, this is good. I gave this as an abbreviation on purpose. I wanted to give you guys perspective on how to draw it. Do you know what this group is? Yeah, this is an aldehyde. I know it looks weird, right? But this is the abbreviation for an aldehyde. The C is bonded to H. The C is also bonded to O. The only way to make that work is to have an aldehyde structure, which means that this is ortho-nitro-benzaldehyde, ortho-nitro-toluene, ortho-hydroxytoluene, or ortho-methylphenol. And here we've got ortho-hydroxyanisole, or ortho-methoxyphenol, or ortho-hydroxymethoxybenzene. Wow, there's so many ways to name it, right? When you've got all those common names for all those little groups, you can pick any of them that you want. Which of these is the most reactive to EAS? Sam is like pointing, but she's shaking her head. Someone want to help Sam out? Sam, point again. What do you guys think? Do you agree with her? Caitlin couldn't see it, but she's pointing this way. Do you agree?
What? Wait, what?
She's pointing
over
this
this
way.
way? Oh, I was like, that's not helping me. No.
You think the most activated, most reactive to EAS is that one? Or somewhere in the middle?
Yes, I think it's that one. No.
Okay. Well, maybe what we have to do then is decide how these substituents impact the ring. We've got 2 ways to do that. Call them electron donating or call them electron withdrawing, or call them activators, call them deactivators. We've got kind of a synonymous relationship now. Activator or deactivator? Activator. Electron donating. Activator or deactivator? Activator. Electron donating. Activator or deactivator? Yes, the weakest, which I think is why a lot of you didn't say it, but it is an activator. Maybe I'll give it a lowercase a, small activator. OH, activator. CH3, activator. NO2, deactivator. Aldehyde. This is a deactivator. Sorry, Caesar?
I just said I would say the activator because of the pi bond.
It's got the pi bond, which is why it's a deactivator. Exactly. NO2, deactivator. So we're looking at some compounding effects, right? 2 strong activators compared to 1 strong and 1 weak activator. How do those pair up against each other? Which is more reactive? The one with more stronger activators. And then I've got a weak activator, a strong activator, and a weak activator, a strong deactivator. Which is more reactive to EAS? The one that has more activation and less deactivation. And then I've got 2 deactivators against a weak activator and a deactivator. Which of these is more reactive to EAS? the one with less deactivating, the one with more activating character. I did not do this intentionally, but I once again have organized it from highest reactivity, which is to say the most activated, towards EAS, and then the lowest reactivity. Another way to say this is highest energy barrier to EAS. But how do these groups activate the ring? Why do they lower the energy of the sigma complex? And where do they tell the ring to be nucleophilic next? What I want to look at next is it's a bit challenging because they really go hand in hand. First, what I want to look at is if we have an electron donating group, how does that impact the nucleophilic character? We've already seen it a little bit. And that will help us understand some of the directing effect. But then we're going to look back at the sigma complex, and that's going to reinforce the directing effect. I never really gave a good header for this, but this was all the activating effect. And now we're transitioning to the directing effect. Okay, I'm going to abbreviate here as EDG, electron donating group. This actually only works for electron donating groups that have a lone pair. So this example, it doesn't count for alkyl groups, but it's still useful to keep in mind. So in the event that this electron donating group has a lone pair that it can push into the benzene ring, we would call this conjugation, a connected series of p orbitals. Then we can draw these resonance forms that say there's a negative charge on this carbon in the ring. Lone pair goes in, lone pair comes out. There's a negative charge on this position in the ring. I think there's something I should address. My electron donating group has just shared a lone pair, which has created a negative charge in the ring. But I can't go from net neutral to net negative in a resonance form. I can go from net neutral to net neutral. So I need to add this positive charge on my electron donating group. And then there's one other resonance form. You don't have to draw this one if you don't want to, because it's actually very similar to what we have in the first resonance form. It puts a negative charge at this position ortho to the electron withdrawing group. And if you really wanted to show it go full circle, then you show this lone pair kick itself back out onto the electron donating group. We've looked at something like this already, correct? We looked at electron donating and electron withdrawing groups, giving us the resonance intermediates. Here's the takeaway. Electron donating groups increase nucleophilic character in general, but more specifically, at the carbons ortho and para to itself. So the electron donating group is already on the ring, but now it is the command center for all of the other carbons of the ring. It gets to tell the other carbons, you should attack, you should attack, you should attack. What positions don't attack? Those positions that are meta to the electron donating group. Nucleophile, 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 not nucleophilic. Does it mean they can't react? No. Just means that they are less likely to react. Are you guys comfortable with this? Does it feel reasonable to say this is why it's a donating, or this is why it increases nucleophilic character here? Now, I don't want to spend quite as much time here, but our electron donating groups, our electron withdrawing groups, they have a similar principle, but I'm drawing in a pi bond, and I think I'll just put like X at the end of the pi bond to represent a hetero atom. Do you know what? Actually, every single time, it's like, except for cyanide, it's an oxygen. So I'll just draw an oxygen for good measure. We know that the pi electrons can be taken out from the ring by this pi bond. And then just follow it around. It's going to go from the position ortho to the electron withdrawing group to the position para to the position ortho again, which is going to sum all together to say that the electron withdrawing group decreases nucleophilic character in general, but it mostly decreases nucleophilic character at the positions ortho and para to itself. I'm not being super clear here with my circles. What I'm circling are the nucleophilic positions. And here's how I'm going to phrase this. Electron withdrawing groups make the ring more nucleophilic at carbons meta to itself.
So it can still react, it's just gonna react most likely in that instead of the other three, because the other three are being decreased.
Exactly. So electron withdrawing groups, they do make it more challenging for the ring to react. But that doesn't mean it's impossible for the ring to react. Those of you that are in lab, last week you ran nitration, which had an electron withdrawing group. Was it impossible for the reaction to proceed? No. In fact, the reaction proceeded so well, we had to keep the temperature below 15 degrees Celsius. So now, if that's how much energy was required, very little energy, was required for an electron withdrawing substituted ring, imagine how reactive benzene would have been. Imagine how reactive toluene would have been. Keeping it below 15 might not have been enough to avoid a runaway reaction. Okay, I really like this diagram. I'd like to keep it up, but I'm going to erase what's underneath it. There is a group that we haven't talked about yet with directing effects. Yeah, the halogens haven't been listed because remember, halogens aren't donating or withdrawing. But we're not going to see it well from here, so I want to do, I want to go a little bit more in depth too. When you look at the sigma complex for a ring that has an electron withdrawing group, there are 3 positions that the group can direct the ring to attack from. The positions ortho, meta, and para to itself. So what happens if the ring attacks ortho, meta, and para to this electron withdrawing group? We're going to look at the sigma complexes that form. The ring has attacked an electrophile ortho to the electron withdrawing group. The ring has attacked an electrophile meta to the electron donating group. And lastly, the ring has attacked an electrophile para to the electron donating group. Now there's going to be a lot of resonance forms, so I'm going to give us a template first. Ortho and para are going to have 3 more resonance forms. 1, 2, 3. The meta position is only going to have 2 more. Without even filling them in, the fact that there are more resonance forms when the ring has acted ortho or meta to the donating group, and only 3 when it reacts meta, more resonance forms is more stable. So why do donating groups activate the ring? They donate electron density. Why do they activate the ring ortho-para? They put on that partial charge character. Also, when they direct ortho-para, they stabilize the sigma complex more resonance forms. So let's show some that we're used to seeing. Pi bond moves towards the positive charge. I am going to do a little bit more abbreviation here, and instead of drawing, no, I won't. I'll show the E and the H each time. It's just better that way. Positive charge moves around. Oops, did do that right. And then what do you know? The positive charge ends up on the carbon bonded to the electron donating group. So what can the electron donating group do? Can share a lone pair with that carbocation. So when the ring is a nucleophile ortho to the electron donating group, the electron donating group can take part in resonance, creates an additional resonance form, stabilizes the sigma complex. There's something more there. Carbocation, carbocation, carbocation. No octets. Electron donating group shares, everybody's got an octet. Which means that this is actually a major resonance contributor. Increases the number of resonance forms, stabilizes it. Creates a major resonance contributor. Now you can go around on this meta position and you'll find that the carbocation never ends up on the position where the electron donating group is. Which means that the electron donating group can never share its electron density with the carbocation. So why do electron donating groups not direct the ring meta? 2 reasons. Conjugation says it's not activating there, and the sigma complex is not stabilized there. 2 reasons. Now, when it's para, lone pair moves, I get this resonance form where the carbocation is right next to my electron donating group. Which means that the electron donating group can share its lone pair and create a double bond. Takes on the positive charge, increases resonance contribution. That's a major resonance form. But how do I get to the last resonance form from there? I just have to do a couple more arrows. I have to say that the electron donating group takes its electrons back. And then the next pi bond in the ring moves up. I don't have to go from this 3rd resonance form back to this 2nd resonance form, then show the formation of the 4th resonance form. All resonance forms exist at the same time, which means you can pick any 2 resonance forms you want, and you can use electron arrows to show how they're related. So I get back a carbocation, not a major resonance contributor, but it does show me my last resonance form. I'm sorry that's so cluttered. Take a picture of it and redraw it when you get home and expand it. I think that this is more meaningful for the electron donating groups than it is for the electron withdrawing groups. Here's just an idea of what the electron withdrawing groups do. electron donating groups stabilize the sigma complex if the ring has acted ortho or para to itself. Electron withdrawing groups destabilize the ring. So not only does the electron withdrawing group make ortho and para positions less nucleophilic, less likely to be the source of reaction, if the ring does react ortho or para to the electron withdrawing group, the electron withdrawing group will make the sigma complex even more destabilized. So we don't want that to happen. The ring doesn't want that to happen. The ring goes for the lowest energy pathway. The ring attacks meta to the electron withdrawing group. Now, halogens. When halogens attack ortho or para to itself, we get a similar set of resonance structures that we saw in the electron donating groups. Positive charge ends up right next to the halogen. Oops, didn't draw my positive charge. Okay, I want to backtrack just a little. Halogens are electronegative, and if they're not electronegative, for instance, bromine and iodine aren't that much more electronegative than carbon, they are very large, which makes them polarizable. And being polarizable can create dipoles even if electronegativity is not very great. This is why halogens are considered deactivators. Their dipole pulls electron density away from the ring. So we would think that they would also be a director like the electron withdrawing groups. Halogens deactivate like electron withdrawing groups, but they direct like electron donating groups, and that's because they have a lone pair to share in this resonance structure. And then they've got another, they've got that last form as well, but again, a major contributor to the resonance form because it maximizes octets. So a recap, electron donating groups and halogens are ortho-para directors. Electron withdrawing groups are meta directors. One last example to mention, which is that alkyl groups don't increase resonance forms. So we kind of made this idea that electron donating groups, they can add these additional resonance forms to the sigma complex, which makes the sigma complex lower in energy and easier to form. But alkyl groups can't actually donate a lone pair. They can't contribute to the resonance. But what they can do they can create a resonance form that is still a more major contributor than the ring would have had without the alkyl group. Boy, let me see if I can squeeze a few more words into that sentence. Which of these two resonance forms is a more major contributor to the sigma complex? Why?
So it's more stable because it's on the tertiary.
Exactly. Here's a secondary carbocation. And here's a tertiary carbocation. So alkyl groups don't stabilize the sigma complex as much as lone pairs can. But they do stabilize the sigma complex by creating a more substituted carbocation. And a more substituted carbocation is a more major resonance contributor. All right, we've got some applying to do. Oh, you know what? Here's a connection between activating and directing. Whichever group is the strongest activator is given the role of directing the next EAS reaction. So here I have a di-substituted benzene, and it's going to go through bromination. Where will the bromine be added? Well, let's do some analysis. What type of group is OCH3? Describe its activating effect and directing effect. OCH3 is an activator. Orthopara director. And what about NH2? Same thing. Activator, orthopara director. Which of them is a stronger activator then? The NH2 is a stronger activator. So who will direct the placement of the bromine? The NH2. I'm actually going to ignore what the oxygen would have done, because NH2 activates the ring the most, which means it stabilizes the resonance structure the most, so it has the directing effect. So what are the ortho and para positions? Here's an ortho position. This ortho position is already taken by the oxygen. And then here's the para position. So there are two products that can form from this reaction. One where the bromine is added para to the amine, and one where the Br2 is added ortho to the amine. True or false, the bromine has been added meta to the oxygen ortho-para director. True. The oxygen is ortho-para directing though. Why has it been added meta to the oxygen? Because oxygen wasn't directing. Nitrogen was. Bromine was added in respect to nitrogen. All right, let's do a couple more problems like this. I'm going to put up 3 molecules. So one of our goals should be to look at a molecule like this and say, how does each group play a role in the reaction in EAS? Is it an activator, a deactivator? Is it ortho-para directing? Is it meta directing? Then we should be able to find the strongest activator and find positions on the ring that are most likely to react. In my first structure, how does chlorine behave? It's a deactivator, but it's ortho-para. The chlorine is the weakest of the deactivators, which is why it is also an ortho-para director. It's very close to being activator, but it's not.
Why is it a deactivator on this one?
Sorry?
Why is it a deactivator on this one?
Halogens are always deactivators,
Okay, I was confused about that.
but they are ortho-para directors.
Okay.
Halogens are not donating groups or withdrawing groups. They have properties of both. They're deactivators, like withdrawing groups, but they're ortho-para directors, like donating groups. Because they are donating groups, but they are also withdrawing groups. Deactivator, ortho-para director. What about the benzaldehyde? Deactivator, meta director. And what about CH3? Activator, ortho-para director. So what positions are most reactive on this ring? Which positions are most likely to be nucleophilic in EAS? The methyl group is our strongest activator. It's actually our only activator, even though it's a weak activator. So its ortho and para positions are the most likely to react. But notice that one of its ortho positions is already taken. Can't go through a reaction there. Fair? What about in my next structure? NO2, deactivator, meta director. SO3H, deactivator, meta director. So these two are going to create positions meta to itself as reactive. Nitro's meta here, nitro's meta is here, sulfonyl's meta is here, and sulfonyl's meta is here. I'm not asking you guys to rank the strength of deactivating groups. So we could say that this structure is fairly likely to react at any of those positions because they're all meta to one of the two groups. All right, now let's skip ahead. In my last one, what is a stronger activator? Tert-butyl or hydroxy? Hydroxy. How many resonance forms will the hydroxy produce in the sigma complex? Yeah, that hydroxy will be able to add its lone pair to give us 4 sigma complex resonance forms. And how many positions will be activated? All 3. Both of its ortho positions are available, and its meta position is available. Cool. Now, tomorrow, what we need to do is look at some reactions and start to take these resonance forms that I drew here and actually demonstrate them in a mechanism. I don't think we need to do a lot because oxygen and nitrogen behave the same way. All of the pi bonds behave the same way. We also need to look at some NAS reactivity. It's going to be much quicker to go through than what we did here. And we'll wrap up tomorrow by looking at multi-step synthesis. How can I take benzene and then do EAS, NAS, and potentially even benzylic reactions to change benzene into a polysubstituted aromatic ring? That's our goal. All right? I'll see you guys tomorrow. Have a good day.